Let f of x be a continuous function on the interval 0, 1, and f of 0 is equal to f of 1. Show that for any integer n is greater than or equal to 2, there exists some a in the interval 0 to 1 minus 1 over n, such that f of a is equal to f of a plus 1 over n. So I'm pretty sure that many people are not going to have any ideas of how to even start with this. First, I'll tell you, this right here is technically just a Calculus 1 question, but I would say it's more for math majors. So today, we are going to have a small taste of Calculus 1 questions for math majors. It's not going to be easy though, but at the end, it's very satisfying. So here we go. I want to show you the thought process first, because if I just show you the proof, you will be like, how did I even start with that? So my thought process is that I saw this first. F of 0 is equal to f of 1, and f is a continuous function, which is a very classic condition. Now let's think about it. In Calc 1, is there any theorems that has the condition that the n values of a function is equal to each other on interval? Well, if you are saying the mean value theorem, technically its particular case, which is the row theorem, then it's kind of correct, but let's observe this a little bit more. For the mean value theorem, what it says is that you are going to have the derivative, it's going to be equal to the slope of the endpoint if the function is good enough. And I'm just going to write down pretty much the main statement. F prime of c is equal to f of b minus f of a over b minus a. And c is somewhere on the interval ab. So the derivative is equal to the slope of the line between the endpoints. Slope of the tangent line is equal to the slope of the secant line. And here's the deal. For the row theorem, is that if you have f of a, it's equal to f of b, which is what we have right here, right? Now, if this is the case, then the top will be 0. So we will be getting f prime of c is equal to 0, which is very nice. And I can show you guys with a picture real quick. Let's say here's f of a, here's f of b, same y value. If you connect the points, what the row theorem is saying that the derivative, it must be equal to 0 somewhere. So that's our c. Now, is this a good approach? Technically, not really, because remember, what's the condition for the mean value theorem? The first condition that we need is the function to be continuous, which we do have it. But the second condition is that the function has to be differentiable. We don't have anything that says that. So I don't think we can approach this right here with the row theorem. And this is not true if the function is not differentiable, because I could have graphed a function like this. Then the derivative here is not 0 anymore. It's not exist right here. So not the mean value theorem, I'll say. Next, what other theorem that also has the word value in the name? Well, of course, we have the average value theorem, but that's for integration. That's way too hard. How about the intermediate value theorem? Now we are talking. IVT. And the general idea is that when you have a continuous function, and that's all we need. So it looks good so far. And the statement is pretty much saying if you have f of a and f of b, then the function takes all the values in between of f of a and f of b. But to me, that is a little bit too hard to use. This is the version that I like much better. Imagine we have an interval and one endpoint is below the x-axis and the other endpoint is above the x-axis. Let's say a and b here. Let's say this is below and this is above. And we have the function being continuous. Then, no matter how you connect the graph, then you will see that the graph must cross the x-axis somewhere at this one time, and that will be our c. So we will have f of c is equal to 0. This is very easy to use. And what's the condition for this? The function is being continuous, and one endpoint is below the x-axis, the other one is above the x-axis. How can we write that down though? Well, they must have different sign, right? So I can say f of a times f of b is less than 0. That's a condition that will give us this. And c will be on the interval a to b. And technically, it's an open interval a to b because you know that this is not 0, this is not 0 because the multiply is less than 0. Now, look at this. We want f of c is equal to 0, but this is what we're trying to show, right? F of a is equal to f of a plus 1 over n. I don't have 0 in this equation. Don't worry. Let's just subtract this to both sides. So we get f of a minus f of a plus 1 over n is equal to 0. Now we are talking. Here, this is the part that we want to observe. So I'm going to start off by calling this a new function, and we'll go from there. Now, ladies and gentlemen, whenever we start writing a proof, make sure we begin by putting down the p at first. It's so satisfying. All right, let another function, let's say g, and I will use x for the input, being equal to f of x, because I'm using x right now, minus, and that will also be x, f of x plus 1 over n. Okay, what's next though? Remember, we have this condition, we have f of 0, f is here, so maybe I want to plug in 0 into all the x's. If that's the case, we get g of 0 is equal to f of 0 minus f of 0 plus 1 over n. So far, so good. Next, we have f of 1. So maybe I need to plug in 1 into all the x's. If that's the case, we have g of 1 being equal to f of 1 minus f of 1 plus 1 over n. But wait a minute. 1 plus 1 over n is not good because this is outside of the interval of our consideration. We just want to have from 0 to 1. I don't know what will happen to this thing right here, right? So, we don't want that. So, what do I really need to plug in though? Now we have these two equations. This is f of 0. This is minus f of 1 over n. Now imagine if this is also f of 1 over n, and then if we add this equation, they will cancel out, right? Yeah, just like a very nice telescoping series. So instead of plugging 1 into all the x's, let's try plugging 1 over n into all the x's, like so. Okay, so far so good. They cancel, and this is f of 2 over n. So maybe let's write down another one. G of 2 over n will be f of 2 over n minus f of 2 over n plus 1 over n, and so on, so on, so on. At the end, I want to plug in g of what? Remember, not 1, right? Not 1. So it's not g of n over n. Let's go a little bit less than that. Let's do n minus 1 over n, because this right here is 1 minus 1 over n. And this looks really good because that's what we have right here. Okay, so once we have that, this is equal to f of, I am just going to put that, so n minus 1 over n minus f of n minus 1 over n plus 1 over n. What's this? When you add them, you get n over n, so this thing right here is just 1, which we have that right here. Very nice so far. Now, I'm just going to add these up and then produce this result right here. When we add them up, the left-hand side will give us g of 0 plus g of 1 over n, and so on, so on, so on, up to g of, and right here, let me just write it down as g of 1 minus 1 over n. That will be equal to, on the right-hand side, this and that cancel, this and that cancel, and so on cancel. This is going to be gone with a term before that. So the only two terms that's left is this. which is f of 0, minus f of 1. Now what's this? F of 0 and f of 1 are equal, so when you subtract them, that must be 0. This is what we have once we have this g function. Alright, this is what we have. And now let's go back to what we're trying to prove. We're trying to show that there exists some a on this interval so that this happens. And by the way, n has to be a positive integer greater than 2, like, just worry about it later. Okay, have a look. We have all these things add up to 0, so what must happen? Well, two cases actually. The first case is they're all 0, right? Well, not really, that's too extreme. We don't need that. We just need some of the terms maybe could be 0, and some of the terms just positive, negative, right? So, case 1, there might be some 0 terms. And this is how you are going to write down a math statement for such thing. I will just say if g of some term, and now notice we have 0 as the input, 1 over n, 2 over n, so on, so on, so on, up to this right here, which is just n minus 1 over n. These right here are the inputs. I'm going to write, you cannot just put down 1 over n is equal to 0. You have to write the general version for that. Let's say k over n is equal to 0 for some k. Because you are using k, so you have to tell the readers what k is. K can be 0, 1, 2, 3, up to n minus 1, just a numerator. So if we have some term that's equal to 0, in fact, we are done, because this right here shows us that g of k over n, which will be f of k over n, minus f of k over n plus 1 over n, and that's equal to 0. Move this to the other side. We see that f of k over n is equal to f of k over n plus 1 over n. And really, we are done, because this is our a. So just say, call this a to be k over n. And because k goes from 0 to n minus 1 inclusively, so this right here, it must be a number between 0 and n minus 1. And of course, right here I have the over n, so technically I should also put down over n, and close interval because we have an inclusion here, k over n, right? So divided by n, so just like that. And then we are done. And that's just case 1. When we have a 0 somewhere. Case 2 is that we don't have 0 somewhere, so we have to be slightly more careful for that. I need to have more space for case 2. Much better. Now, for case 2, we are supposing that none of these terms is equal to 0, so we can write this down. G of some index, let's say I, over n. These right here, they are all non-zero. And I will have to indicate that for all I from 0 to n minus 1. Now let's think about it. If all these terms are not 0, but they add up to 0, then what must happen? Well, we must have some negative term and some positive term. But we're not saying that like this is exactly the opposite of that. No, we are not. We're just saying some term is positive and some other terms are negative. That's all we need to say. So I will just write this down just to be making this more clear. Then we must have, I'll just write this down here. Then we must have a positive term and a negative term. Now, why do we must have two terms? Well, n goes from 2, 3, 4, so this is where we can use the n. So that's that. And now, I wrote down we must have a positive term and a negative term. So I will just call them. Okay, I use I already, that's just j and k in this case. So I will say g of j over n. Let's say this is the positive term, and k over n is the negative term. Now I have to specify what j and k are. Once again, they will be going from 0 to n minus 1. Now here is some technical part. I will write this down first for 0 and n minus 1. Let me write down j first. And then, here's the question. Do I know that right here, does the positive term that goes first or the negative term that goes first? Does it matter? The truth is, it doesn't matter, right? So right here, I'm going to still say that the positive term that goes first. To do so, I will just say j is less than k. That's okay. And right here, to be technical, you will have to say without loss of generality. Because today, if the negative term that goes first, I'll just switch it, the rest will be the same. Don't worry about that. But that's just how you write down the technical proof for it. Now, once again, make sure that j and k are not equal, so just a strict less than, but j can be 0, k can be n minus 1. So far, so good. What does this look like? That looks like exactly what we mentioned earlier, right? Where we can use the intermediate value theorems. So here we go. Things. First, let me mention that when you multiply this and that, you get negative. So I'll just say g of j over n times g of k over n. It has to be less than 0 because positive times negative. And, well, before we mention intermediate value theorem, make sure we mention the function is continuous. Is g continuous? For sure, because f is continuous, and the difference between two continuous functions has to be continuous. So just say, and g is also continuous on our interval. Okay, from here, we can say by the intermediate value theorem, there is some number a, and a is a number in between of from here to here. And this is where that you really have to mention that j is less than k, so that I can write a as an element of j over n to k over n. Smaller number goes first. And for when you use the intermediate value theorem, this right here it's not including because it's just a strictly less than, but because this interval from j over n to k over n is just a subset of this. So let me write that down. Why though? Because j could be 0, k could be n minus 1, and when you do the over n, you get exactly this. A belongs to this right here as well. So you can continue by saying such that what? This times this is less than 0, so that means we must have an element somewhere on this interval that is equal to 0. Now, when g of a is equal to 0, g of a is this thing right here. Plugging a here, plugging a here, it's equal to 0. Move this to the other side. So we get, that is, f of a is equal to f of a plus 1 over n. That's it. All done. Put box, shading.